Today we're starting chapter 6, astronomical instruments, mostly telescopes. We'll look into principles behind telescope, ground telescope, and later space-based telescope. So these are the first two sections. Telescopes today with the SLOs, learning objectives. First, we'll look at basic components of telescopes and how they have evolved into telescopes today, and later we'll look into how light collected inside the telescopes are detected or stored for later use, and the challenges that we face to run either the ground-based telescopes or the space-based telescope. Why we need telescope in the first place? You may not have realized, although we see hundreds of stars in the night sky, definitely not from big cities that we live in. We have lots of light pollution. That light pollution causes or blocks the light coming from the distant source, like stars or even galaxies, and we don't see them. It's the pollution, and it's definitely not helping the astronomers. In any given time from around the Earth, only about 9,000 stars are visible to the naked eye. Even without the light pollution. But we know now that there are billions of stars within the Milky Way galaxy. So how can we detect or observe those stars with, without our unaided eyes simply cannot see? And here is an example of a space-based telescope. You all have heard of the mighty Hubble Space Telescope. It was the most powerful space-based telescope since it was launched, and it is still. However, the story is changing. The history is being rewritten. You may have heard of James Webb Space Telescope that we will look into today briefly. Okay, there are three basic components of a modern system of measuring radiation. We call it radiation because now you know radiation consists of the whole spectrum of wavelengths of light extending from gamma rays to radio. In the visible portion that we see, we use optical telescope. Like this one here, this is based on the visible light. We're looking at Orion region, Orion constellation, and this is the Orion's belt. So by using a visible telescope, or this part of the sky, this constellation looks like this. On B here, this is the same region now looked by a different lens, and now that lens records the X-ray coming out from that region. X-rays, not visible light, but X-rays, little stronger part in our spectrum. And this one here on the third one is the infrared radiation. when things get hot, hotter objects emit infrared radiation. Right, our body right now, if my eyes could detect infrared radiation, you'd all be glowing like this one here. The gases around this region here absorbs the radiation from the stars, from galaxies, and they emit that infrared, and the infrared camera in the infrared telescope detects this region in this color. And again, the basic components are telescope. They collect light. Simply, it's like a bucket gathering water. They collect light, they collect photon, and that photon are directed now into instruments, where those instruments can show different wavelengths of that light collected, wavelengths of those photons collected, and now those photons are directed into certain part of the detector within the telescope or away from the telescope, and those detectors detect those radiation at different wavelengths. Like this picture here can, be taken with one telescope, and the X-rays can be directed to one detector where it puts out this image, and the infrared waves can be directed to another device which puts out this image here. But it didn't start this way, of course. Look at the first telescope built by Galileo to observe the planets, the wanderers, what they called, Mercury, Venus, Mars, Jupiter, Saturn. He even looked the moons of Jupiter using this simple device in 1610. Okay. However, this device was, Galileo used it in astronomy extensively. There are other claims from these inventors, Hans, Zacharias, Jacob. They filed for the copyright as well, credited to the invention of this telescope around 1608. They have patents to it. So maybe we should not give entire credit to Galileo, but Galileo definitely used it for the astronomical purpose. And before telescope, there were observations made, and we still do it today. And we see something, we write down, and for that purpose, certain places were built, like this Machu Picchu and this Stonehenge. But this was all based on what you see, whatever eyes could gather, and whatever you see, then you had to write it down, log it in a book. Or creative people, sometimes they draw and keep that as a record. And this telescope here, a wooden piece, maybe a bamboo, had some lenses inside, later evolved into some of the biggest telescopes. So how does telescope work? Simple. It collects light from the astronomical sources, could be stars, galaxies, nebulas, and as such, and all those light are focused into certain point where now we place a detector. Detector collects all that light and forms an image. And you see the first telescope was pretty thin, so the area of the lens was thin, small. Later we realized if we can increase the size of the area, more light can be collected from a fainter star. We only see bright stars, yet stars that are much farther out, the galaxies that are much farther out, they give out very faint light that we cannot see. But if you have large enough area and increase the exposure time, meaning collect the light, not for a few milliseconds or a second that our camera does, these telescopes they open up for hours, days, basically collecting the light coming in and produce better high resolution, crisp images. And again, larger area means more light can be collected. For example, here, if a lens has 1 meter diameter versus 4 meter diameter, the calculating the total light collecting area, its simple area is pi r square, pi times radius square, but radius is after diameter. Put in that formula for 1 meter telescope has 0.79 meters square, 4 meter telescope gives 12.6 meters square. That's a factor of 16 difference. So having 1 meter diameter telescope compared to 16 meter diameter, 4 meter diameter telescope can can collect 16 times more light, hence produce better image, high resolution image, high quality image. Lens have certain properties, and there are different types of lens. Two mostly widely used are the convex lens and the concave lens. Convex lens have these, this is concave, see this is convex, the bulging edges. So when light, the parallel light, usually the light coming from distant source, sun or other stars, are parallel by the time they reach here due to the distance they travel. These parallel light rays are converged by a converging lens or convex lens to a point called a focus, or a focal point, focus. So the light rays here coming from distant source, they are converged. So an image is formed at the focus by a convex lens. The other lens is diverging lens. It diverges the light rays, but we can have a diverging mirror instead. So if we polish one side of this diverging mirror here, polish it on this side, so it reflects back to, again, its focal point where the image is formed. So we can have a converging lens telescope, or we can have a telescope that have mirrors in it. But again, these are some of the technical terms. The focus is where the parallel light rays are converged. And this depends on the size of the lens, thickness of the lens. This means the length, distance to the focus, which is called the focal length, from the lens to the focus. This is called focal length. This length can decrease or increase depending on the size of the lens itself. And so now basically for inside a telescope, here the starlight enters the opening of the telescope. Like this is the starlight here. The ray model is given down here. This is all starlight entering a convex lens, which converges the light to a single point called the focus. Here, this lens has a focal point around that region here, but if we don't stop it, then they crisscross each other and they reach another piece here that's designed to magnify. This is the eyepiece here, and the image that's formed here, emits light rays that are magnified by another lens, and that's how, or that's an example of simple refractor telescope. Here, light rays entered from one end, it converged to a focus where the image is formed, and now that image can be further magnified by another magnifying lens, convex lens. That's this type of telescope is called refractor telescope. It refracts, lenses refract the light, because lenses are, they are not opaque. They transmit light. The other type of telescope is the reflector, like this one here is a concave mirror. This is polished on the back side, so it reflects light. So that's why it's called a reflector telescope. It has a very wide opening in this edge here, like the Hubble Space Telescope has a very wide opening, and bigger that opening, more light can be collected. So the mirror surface area of the mirror has to be bigger area, more light, and all the starlight that hit the mirror here gets reflected, and based on the this curvature here, right? This curvature here has certain focal point, meaning all the parallel rays that come from a distant source, when they hit this curvature or the concave mirror, they reflect back to a point, they converge back to a point or at its focus. And that's where the image is formed. And to view it, another little trick, place another small mirror here, because now all this light rays is converging to a smaller area. Put a small area mirror there which reflects back towards another opening, and there we can put a magnifying glass, and we can observe that distant object. Could be a star, could be planets, or even galaxy. We can see our nearest galaxy to the Milky Way, Andromeda, using such telescope. Okay, going from a very simple, like half-inch diameter telescope, within 100 years, 200 years time, in 1948, U.S. astronomers built telescope with 5-meter diameter, going from 1 or 2 inches to 200 inches long, and that's the Palomar Mountain in Southern California. This is not the Palomar one. This one is different. This is the VLA, very large telescope, built by ESO, European Southern Observatory. This is situated in Chile Mountains, and this one has the diameter of 8 meters. So very large collecting area. It's a concave mirror. Light falls in that 8-meter diameter mirror, and they converge to a point, producing some of the best images we have seen of planets in the solar system, the galaxies, the star clusters, the stars, nebulas, and whatnot. And that's 8 meters. There are 10 meters. There is 50 meters that's being proposed. So it's only getting bigger and better. This one is the Palomar in Southern California here, and there is a challenge. When you bigger mirror, back then with the technology, it got very heavier too. This one was 14.5 tons for 5-meter telescope, and when it's that big, it can sag due to gravity, due to its weight, and distort, and so they had to build another 100-ton supporting system. Here, this was in 48, but later, after 50 years or so, there are better materials were found, a better technology where thinner mirrors could be built, like this one, Gemini North. This is 8-meter wide, and lesser equipment, lesser steel to hold this in place. I was at Gemini North here in 2017, no, 16 December, and I had the opportunity to tour around the Gemini North. This is in Mauna Kea Mountains in the Big Island of Hawaii. So you see, the telescopes are getting bigger, and bigger means better in terms of telescope because of the size. It can collect more light, it can collect more faint light, and it can collect light coming from much farther galaxies. Right? We're talking about millions, billion light years away. And this is what this telescope is designed, the James Webb Space Telescope, the most expensive telescope ever built, more than $10 billion. It was launched a few months ago. It is in the process of calibrating its equipment. It has these huge hexagonal mirrors. These are gold plated because you want mirror with best reflecting property. The mirrors that we have reflect about 95–96%. Rest is observed, so the information is lost. So whenever light is very faint, and we're not faint because we are shined by very bright LED lights. But when this thing is in space and you're trying to collect light that has been traveling for last 12 billion years, that's faint. So you want to collect more of that faint light in a larger area, and that's what this thing is designed for. You don't want any of that faint light to be observed by the mirror. So you want all of it, 99.99% of it, to be reflected back to the detector here. Okay, and this is the most technologically advanced telescope that we have. You may have seen its first picture during the alignment process, and I think it'll go into full commission starting July or so. And again, the goal is to find or to detect the light from the earliest stars that are farthest away from us. The land-based telescope, we have certain challenges for using this telescope. And one is the weather. Okay. Especially if we are doing optical, in the visible range, we should be able to see the light should be able to pass through the atmosphere and hit the telescope. But if it's rain, wind, cloud, and so that's the challenge. We have to overcome that. And so the best place on Earth to build telescope is where it rains less, where the weather is fairly constant. It can be hot because this one here is the desert in Chile, Atacama Desert. I don't think it has rained there in the recorded history. No clouds. It's at much higher place. Very dry. Dry weather is good. If it has moisture, it has atmosphere. It has moisture in the atmosphere. The water vapors. Those water vapors can absorb the light coming in and emit its own infrared radiation. And that distorts the image that you're trying to take. So dry is better. And of course, it has to be much, much farther away from the city. As a matter of fact, to have a good night sky, visible night sky, if you really want to enjoy the night sky, you have to travel as far as 100 miles from the city. Okay, so that's why this telescope, like our biggest, best in Texas, is what's the West Texas Observatory, McDonald Observatory in West Texas by the Guadalupe Mountains. That's like 400 miles from here. We do have one observatory. And that McDonald Observatory played a critical role in finding, detecting planets, exoplanets that orbit two stars, a Tatooine-like planet called Gamma Cephei. We'll look into that planet and observatory when we do exoplanets. And finally, the turbulent air, because the air is moving fast, there can be turbulence in the atmosphere, the molecules of the air, and that distorts the image as well, and resulting in the blurry images of the stars or galaxies. Astronomers call this term a bad seeing. However, there's a way to get around this turbulent air. This is the highest resolution, clearest image of a Jupiter taken from the Earth's surface. And nowadays, again, we can get rid of that turbulent air by something called adaptive optics. It's like AI, artificial intelligence. Computers are connected, sensors are connected within the telescope mirror, where those telescope mirror can be twisted and turned in a way to compensate for whatever the turbulence is. If turbulence changes, if turbulence causes the this image to distort by some degree, then we can adjust that mirror, or the computer detects that, and computer automatically adjusts those mirrors to compensate for the distortion, and hence produce a sharp image in the detector. And that field, or that technology, is called adaptive optics, meaning the optics adapts itself to compensate for any external error. And again, resolution refers to the precision of details present in an image. High resolution, you can expand it more, you can zoom in more, and you can see more details of its structure in the Jupiter or other planets, or even moon. Now let's look at the detectors itself. What's there in the detector? And other type of telescope like radio telescopes. In 1990, this person here, whom I had the honor to meet with in 2010 in Portland, Oregon, his name is George Smith. He was working in Bell Labs in New Jersey, I believe. And he found a way to store the energy excited by the photons, and that energy which is carried by the electrons. Okay, let me rephrase that. He invented something called CCDs, charged coupled devices. And how that works is, whenever a photon, a light particle or a radiation particle, whenever a photon hits a surface, that surface, or a detector, a metal, that surface has electrons. That photon energy, whatever energy the photons come with, again, photon is the light particle. So right now your body is emitting out photons, that's why I can see you. Those light particles, those photons are entering through my eyes, and it's hitting the receptor inside my eyes in the retina, and that excites the electrons. Those electrons charges move to the brain, and my brain interprets that energy and makes me able to see. In the same way, the photon that hits the plate excites the electrons, and that excitation energy is carried by the electron and is stored somewhere in the detector. And when it collects all the different photon energy, it's able to store basically a picture of that object. And this CCD revolutionized everything. Remember the tape camera that you had a film, you had to have a film in it, and when light enters, it has sensors, photographic sensors in it, chemicals in it. That's one technology. But with CCDs, we didn't need a film anymore. That's when we started to get all these digital cameras. Our phones have it. These days, everything has CCDs. And so for that contribution, he was awarded Nobel Prize in Physics in 2009, George Smith. And that's what we use in the telescope. The telescope, the mirrors, lenses, they collect light that they form image, but those are directed somewhere. They have to be detected and stored for later use, right? And we use CCDs like this one here. They have grown, of course, the efficiency has increased of those CCDs. And as a matter of fact, each place where the radiation is counted, one photon is called a pixel. One hit is a pixel, and modern detectors can count the photons in millions of pixels, megapixels. When you say your camera is, 10 MP, 10 megapixels, when you take a picture, it's recording 10 million pixels per, usually it's per inch. Inches square area, there are 10 million dots. And more is the pixel is like the grid, more grids, more resolution, higher resolution. There are also infrared observations. Hot objects emit infrared radiation, not just hot, even any vibrating charges can produce infrared radiation. It's part of the whole spectrum, electromagnetic spectrum. Your normal body versus it's covered in a thin plastic, but the plastic does not emit any heat or infrared radiation. But if it's looked through a camera that can detect infrared, a person would glow and seem like this. Even the radiation coming out of the hand are detected. And again, infrared is a heat radiation. The one challenge with building infrared telescope is that since it detects the radiation from hotter object, the telescope itself has so many electronics, it's constantly creating some form of heat. So that heat can be detected within the lens and can obscure the image or the actual radiation that you want, infrared radiation that you want from distant light, distant stars. When you're trying to measure the infrared radiation from a light source that is 10 billion light years away, but before that light can be detected, you have that background noise due to the heating telescope itself. Okay, and the solution is to that is there are two ways. we can prevent that. For the Earth-based telescope, that this telescope can be covered in a very cold surrounding, cold temperature. We can actually dip it inside a helium or liquid helium towards absolute zero temperature. So that radiates least amount of infrared radiation. That's like reducing the background noise, the unwanted radiation, and only looking at what you want, which is the infrared radiation coming from a distant source. And the other way, again, we can take telescope into space, like James Webb Space Telescope. But even there, we have a challenge because the sun, this space, we're not getting too far from the sun. It's within the solar system. But the sun rays, the radiation from the sun can strike the telescope itself and cause that unwanted infrared radiation. So for that reason, there are these foils. These are almost football-sized field foils. Again, the telescope always faces away from the telescope, and the foil blocks the radiation coming from the sun. And there are layers of foil, works like an insulation. So even some radiation enters through the first layer, the second layer stops it, third layer stops it, and there is no radiation passing through it. And out in space, in one of the Lagrange point, in space, that far, it's very cold. And so cold, whatever radiation is blocked, so it's the best place for a telescope like this one to observe any infrared radiation coming from the light source from galaxies, the stars that are 10, 12 billion light years away. That's the whole visible universe. And the spectroscopy, it's a device, that converts a light ray into different spectrum of light. For example, light source is collected here by a lens. It's converted and sent to a small slit. And it converges here, goes through a slit. Of course, after that focal point, it diverges again, but we have a lens, collimating lens, that sends this light source coming from the image here into parallel light rays. So this is just opposite here, opposite to this lens. When the light comes in parallel and enters a convex lens, they converge to a focal point, but the light source coming from the focal point, when it hits the converging lens, they emerge parallel, opposite. So now these parallel light rays are passed through a prism, and light rays get refracted here because the light rays have different. This light ray consists of multiple wavelength light, because visible light extends from red to violet. Depending on the energy of the photons, they refract differently, they bend differently, and so basically we are separating lights with different wavelengths, and they are sent to a different detectors. If you want to measure something in the red, you put your detector in the red image, red detector here, which forms a red image, versus green, versus violet, and so on. So here are multiple detectors that have CCDs, or photographic plates. And that's the spectroscopy. And one challenge is that because the light source is spreading out, the photon count gets decreased. This light source, now we are breaking into multiple colors. And so same amount is now being detected by multiple detectors, but each detector has very less amount of photons compared to these all photons here that enters the collimating lens. So for that purpose, we may need to increase the size of the lens, more area, more light, or increase the exposure time, the detection time, or the time that we collect the photons. We may have to increase that significantly, or both. The radio telescope so in our electromagnetic spectrum, this is the radio range, very large wavelength, longer wavelength, small frequency, and as it moves towards the gamma rays and X-rays past visible light, this is our visible section, and this is our infrared section here. This is gamma rays and X-rays. So we can build telescope to measure each section of this spectrum to detect light or photons of each wavelength. Optical means visible, okay, infrared, and now accidentally a radio telescope was built. Antennas, same like your radio antenna, your TV antenna, you have a car antenna above in your car. These antennas, they detect these radio waves coming from your FM station, and these waves carry energy. These radio waves transfer that energy to the electrons that are in your antenna, and those electrons carry that energy to the machine in your radio, called that decoder, because it's decoding the sound wave, the voices, the songs, the music that was converted into radio waves. Your antenna receives the radio waves. That excites the electrons in the antenna. Now that electron, which is electrical, which carries electrical waves, electrical energy that has to be converted into sound waves. So you have a decoder, and that sound waves is sent to a speaker, and you hear the voice. So there is a coder and decoder. First, it has to be coded. Sound waves has to be coded into electromagnetic waves. Electromagnetic waves are decoded into sound waves. And during that process, this guy, 1930, Jansky, was receiving these radio signals, not being generated by anyone on the Earth. As a matter of fact, later he found these radio waves coming from other objects in the sky, from other stars, because colliding stars, the supernova explosions, and there are other events that produce these radio waves hundreds of light years away, and they travel everywhere in the universe. Some of them happen to hit his devices, and he was getting that static radio signal all the time, and hence a birth of radio telescope happened in 1930. Later on, scientists more formalized it, make it more precise. Just like the visible light, when light ray enters a concave mirror, it reflects back, or a mirror, you can see yourself because the mirror reflects light, that's a visible light. These telescope Radio telescope, X-ray, gamma rays behave the same way. Any wave in this spectrum here gets reflected, like this curvature here of this antenna here. The radio waves coming in hit this curvature space, and they reflect back to a focal point. All the radio waves hit this curvature here, and they reflect back to a detector here on the top. And that signal is sent to your electronics to the CCD, and pictures like this can be created. This is of the galaxy called Cygnus A. The radio signal coming out of the galaxy. And of course, the colors are added because the radio, we don't see it, but based on different energy, we can add artificial colors to it. For example, in this case, red regions are the most intense, and the blue the least. And this is 160,000 light years long, this distance here. And you have seen other popular radio telescope like the Puerto Rico, which collapsed, I think 2 years ago. It's no longer operational. This used the same technique. This disk here, the radio waves coming in, hits the disk, and all these radio waves are reflected back into a detector here on the top, and that signal is taken out for processing. This is a good example of radio telescope. There are many other. This one is Atacama in Chile, northern Chile. These all disk here, they all detect radio waves coming out from, not just from solar system. The interaction between our nearest, largest planet, Jupiter, and the moon, that interaction, the Io, Jupiter's moon, Io, and the Jupiter interaction creates this certain radio wave signal, very peculiar. And that signal can be detected here on Earth. We can hear that static sound, and not just from our planet, from distant galaxies as well. And we can form an array of such telescopes because it only collects certain, it's limited. So if you want to collect more light, it's like increasing the surface area of a mirror. This is called very long baseline array, and some radio telescopes are placed in Hawaii, in the Caribbean, from Maine to Southern California to Northwest mainland US. And so all of these data can be collected at a point and further analyzed. The example of radio telescope. Okay, so I'll stop here. Next, we will look at the observations that are made outside of our atmosphere.